This is a remake of video number 7. The subject matter is a special case of a second order ordinary differential equation known as the Euler-Cauchy equations. This is section 5 from your textbook. So I've chosen to also select some information. It's very similar to what's in the textbook. Sometimes I think your textbook gets a little overemphasizes some of the mathematical formalism, and you sort of lose sight of the forest for the trees. So I've chosen to take some of this information from the following Wikipedia site, and I just want to acknowledge the site and the author. I think it's written in a way that maybe flows a little bit easier. So this is a special type of differential equation that looks like this. You have a second order derivative in y with respect to x. That's multiplied by x squared. You have a first order derivative in y with respect to x that's multiplied by x and some constant a. And then you have y multiplied by a coefficient b. Because we have some powers of x that show up in this equation, we're going to assume a trial solution that y is some polynomial in x. And this is not a bad assumption because since we have powers of x running around in the equation, we would assume that in taking some derivatives of y, we might generate some powers of x that might satisfy this differential equation. So we're going to assume that y is equal to x to the m. And then following the way a lot of solutions to differential equations are done, we're going to take our solution and substitute it into our differential equation and see what we get. So when we substitute the first derivative, we'll get mx to the m minus 1. That'll go in for dy dx. And then when we take a second derivative, we bring down this second power here. And so we get this expression, and that'll go in for the second derivative of y with respect to x squared. So when we make these two substitutions, we get this expression here on the equation that's the second one up from the bottom. And then we can rearrange this a little bit by pulling out a common factor in x. So notice here, this x squared and this x to the m minus 2 combine to give us x to the m. We have x to the m here. We have x to the m. So x to the m really appears as a common factor. And we're going to use the old trick in solving equations that if we have something that is equal to 0, the only non-trivial solution is if all of when we pull out the common factors, if all of the coefficients become 0. So that gives us the following equation, which is just a quadratic equation in m. Remember, m was our assumed solution power. So we have this quadratic equation in m once we've rearranged, and we want that to satisfy 0. So obviously, we can use the quadratic formula to solve for this, and anytime you use the quadratic formula to solve for anything, you have three possible cases. One is where you have two distinct real roots, m1 and m2. One is where you have a perfect square, which would generate a real repeated root m. And the third is where you generate a complex conjugate pair, a plus or alpha plus beta times I. In electrical engineering, we might call this alpha plus j beta. To distinguish alpha and beta are different from a and b. The particular solution that you get from case 1 through 3 depends on obviously the values of a and b in the differential equation. So in case 1, where you have two distinct roots, remember we assumed a solution x to the m, and we now have two possibilities. So in keeping with differential equation theory, those two possibilities form a basis, and so our most general form of the solution will be a constant times the first function plus a constant times the second possible function. In case 2, where we have a double root, we generate this x to the m power, but one of the terms in the equation is multiplied by the natural log function. So this is very similar when we had differential equations that had basis solutions of e to the st, and if we had a second order root in s, we generated a term that had x multiplying e to the st. I think you can see if you were to take that solution and take the natural log of everything, you basically would generate this solution more or less. So in case 2, where you have a real repeated root, or a perfect, that would mean this equation would be a perfect square, we would get this solution. And this reduction of order, that's basically the same thing you do when you have if we were solving a second order differential equation with unknown coefficients, constant coefficients. So in case 3, this would be the case where you have complex conjugate pairs. We basically generate an alpha and a beta, and so you would have x to the alpha, which constitutes the real part of the solution, and then the cosine of beta times the natural log of x. That multiplied by c1, and the same thing, only the sine multiplied by c2. So alpha is the real part of the solution to m, and beta is the imaginary part of the solution to m. C1 and C2 would be real constants. So we generate these three different types of roots. Then we have some figures basically that illustrate what solution curves look like for Euler-Cauchy equations, and those are accredited above, licensed in the public domain. So the first case is if we have two distinct real roots. You can see x, we have various powers of x here plotted, or various, y equal to various powers of x represented by the different colors. And here's x, and then remember, typically in a general solution with real roots, we'll be getting a sum of two of these. So you would have whatever your first and second, your two different powers are, you would have the sum of two of these curves weighted by a constant. Case 2, where we have a double root, this is just some examples of the natural log of x times x, the natural log of x times x to the 1/2. So just different powers of x times the natural log of x, representing what that one portion of solution in the double root looks like. So in the general case, if you have a double root, you would have one of these curves added to one of the curves on the previous slide. And then finally, and this is taken from your textbook, just an illustration of a possible equation where you would have complex conjugate roots. So this Euler-Cauchy equation, notice that we actually have a constant plugged in here. So this is our equation. And then if you then find the auxiliary equation, it's going to look like this. So this is your 1 minus 0.6 term right here. When we solve this equation, we get a set of complex conjugate pairs, 0.2 plus 4i and 0.2 minus 4i. And so taking those complex conjugate pairs and substituting them into our general solution form, it would look like this, where x is our variable, 4 is a constant, 0.2 is a constant, and then a and b are constants of integration. So we would be able to solve for a and b if we knew what? If we knew two initial values. So we would need an initial value on y and on its first derivative in order to get a solution for a and b constants. Otherwise, we have a general solution. So those are the three cases. This is just an example of a plot also taken from the same Wikipedia site, showing both sine and cosine of 4 times the natural log of x times x to the 0.2. So those equations would look, or the plot, those solutions plotted would look like this. And notice that this is looking a little bit unstable here. X is trying to grow in magnitude, but it also looks like it's going to settle out, approaching a final value. So your textbook basically has exactly the same derivation where they come up with this auxiliary equation, and the only difference here is that M1 and M2, we have a couple of equations in your textbook that put M1 and M2 in terms of A and B, which were the constants, the coefficients in the original equation. So I guess if you wanted formulas for M1 and M2 in terms of A and B, you can get those from this particular point in the textbook. And then they continue on exactly the same path as what came from the Wikipedia source, where you do have two real roots that would give two real solutions, a power solution, a real double root that gives the power and natural log solution, and then finally the complex conjugate roots. So Euler-Cauchy equations, some importance in engineering because they do represent some physical problems. Generally not a lot that we see in electrical engineering, tends to be more mechanical engineering oriented, but nevertheless they do represent um, some engineering problems of some physical significance. So this is just an exposure to the fact that there is this family of equations. They do generate solutions that are powers of x and the natural log. This is kind of everything summarized all in one page. The three types of roots that we saw in the previous separate slides kind of put all on the same page together.